Okay, so let's continue now. So look at this. So now I have an opportunity to make some drawings. Okay. So you got my good friend got coffee. So you happy?
Yeah.
Keep on asking those outstanding questions. Others, remember there was some discussion about the candies last week. So here's a candy for you. So now you can relax a bit. There's more. So make this go around. Yeah, I wasn't sure what kind of candies you like, but maybe you can later let me know what is your preferences. Okay, now we were in this line. Here comes something very important, because there is consequences when moving from not a degrees of freedom to moral degrees of freedom. Remember, this is how the equation of motion originally looked like. And now I need to make this a bit bigger. This is how it looked originally. All right? Now this is the one that includes a lot of degrees of freedom. And I would like to leave this lot of degrees of freedom and move to moral degrees of freedom. How it happens? Well, it happens with this relation. You know, my nodal degrees of freedom and my corresponding modal degrees of freedom are related with help of assumed deformation. So this is a matrix that shows what are the different ways that the structure can deform. We will take a look at the details in a second, but this is roughly speaking ways that the structure can deform. This is here telling, thank you, telling what are the amplification, what is a contribution of each one of the ways. Amplification associated to each one of the ways. Okay, so now if we're gonna move from these nodal degrees of freedom to modal degrees of freedom, this comes with the very pleasant consequences. And the first important observation is that this relation here is a linear relation. Is meaning that also the accelerations can be written like this. Okay, so let's move from, let me take this off, from these nodal degrees of freedom to modal degrees of freedom. So first thing to do is that, you know, let's use this relation to see what is a consequence of this equation. So equation can be now written like this, P dot dot, because it's a linear relation plus elastic forces that are then expressed in terms of modal coordinates. Then this is equal to an external Laplace force. Let's just put it this way. Now this is not yet acceptable. And it's not yet acceptable because, you know, inertial forces and elastic forces are expressed in terms of modal coordinates. External applied forces is expressed in terms of nodal coordinates. So they don't match. So I have to make them match. I can make them match by multiplying this equation one more time with a transpose of the ways that the structure can deform. So then here comes transpose. Oh, excuse my writing, it's very unclear. But use your imagination to follow me. And here, this is transpose. And when I write this in a proper way, the equation of motion look like this. This is my equation of motion, expressed in terms of modal coordinates. Now, if these deformation modes are orthogonal, like they are in a case of when you get out from eigenvalues, it comes with another very significant consequence. Another significant consequence is that these modal coordinates are not coupled. What that means? Well, it means that if you look at the original nodal coordinates, these stiffness and mass matrices are not diagonal matrices. They are block diagonal, but they are not diagonal matrices. Meaning that you cannot solve one degrees of freedom without knowing anything about other degrees of freedom. It's coupled problem, at least loosely coupled. Here, they are not coupled at all. So you can take any model coordinates you want and solve it without knowing anything about others. And that's a beautiful thing. So, what is the consequence eventually? Is that this representation of inertia, which is associated to modal coordinates, is actually, depending on the scaling, it can be identity matrix. Stiffness associated to modal coordinates is a diagonal matrix where these eigenvalues, not in a power 2, but eigenvalues in the square root, are located in the diagonal components. Only thing that is left to say is this. Beautiful. It's just, I mean, that is, I'm about to start crying. Look at this, we moving from nodal coordinates to modal coordinates, we thought that we can just reduce the size, and that's what we did. Plus, we got this super nice mathematical feature, meaning that coordinates are not related. Is this how many wonders we have in the world? 7? Is this like 8th wonder in the world? Almost. Could be considered as 8th wonder. This is special thing. This, learning something like this is a once in a lifetime experience. You feel it? It can get into your mind like, oh my God, really? Yes, really. This is what happens. Okay. Now, let's look at the details. Let's look how is that we can actually carry out this eigenvalue analysis. I have here a very simple structure as an example. This is one of those spring elements of the spring structure that is modeled by using, let me see, 1, 2, 3 elements. And I'm constructing the mass and stiffness matrix associated with the structure. Stiffness matrix, I learned how to divide this stiffness matrix. And here is my first stiffness matrix. With that stiffness associated to first matrix, this is the one that is associated to second, and this is the one that is associated to third. Look at this. This is where they are overlapping, and that's the nature of the finite element vector. Similar way, I can construct my mass matrix, and this is all it is. All right, so I have components needed to carry out this task. Now I'm going to use a symbolic math to compute the eigenvalues. Real life, you don't do that because you want to do everything numerically, not symbolically. But just to keep things simple, I'm going to do this symbolically. Okay, first task is to compute eigenvalues. What is an interpretation of eigenvalues? Natural frequency of the structure. When you're introducing these forces or arousing the motion in that frequency, then the amplitude will theoretically goes to infinity. All right? So I'm going to take my stiffness and mass as it is shown in this equation, and then in the front of the mass I have my omega power 2, which here is a little bit confusingly denoted as a lambda. Lambda here is equal than this one here. Those are the same story. Now, when I'm taking determinant out of this equation, setting that to be equal to 0, I will get the equation that is shown here. Now, my task here is to solve lambdas. So there's a lambda, 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 and lambda. So obviously this is a 4th order polynomial. How many times this goes through the 0? 4 times. Correct. 4th order polynomials. 4 times goes through the 0. So what are these points? When I'm solving the lambda, so lambda has a 4 different solutions because of the 4th order polynomial. Okay? So the first one is a lambda equal to 0. Lambda equal to 12. These are just the values. Lambda equal to 60. Lambda equal to 120. And this is a way that you can count natural frequency if that's what you're looking at. First one is 0. Because of what? Why did it 0? What is the physical interpretation of that? Candy? 2 candies. You can get 2 candies if you can answer that correctly. Simple thing.
Rigid body mode.
Because of the rigid body mode. It's a rigid body mode. That's what it is 0. Okay. Now, others are values. You know, what is it they stand for? Well, we don't need to worry about the physical interpretation. Those are the natural frequencies of the structure that are associated to ways structure will vibrate. Structure will vibrate. Let's take a look. Okay, first one. Let's look. What is an eigenvector that corresponding to eigenvalue lambda equal to 12? How can we find it out? Well, let's use this equation. Let's substitute 12 here, and then we can get 4 equations. We can get this one here. Once I do this matrix multiplied by a vector that is unknown, I can get 4 equations, 4 unknowns. All right? So once I'm solving the unknowns, and the unknowns again are these ones. Once I'm solving them, this is how it looks. So this is a way structure default. Not about the absolute responses. So the worst mistake you can do is that you can measure absolute responses that are coming from the eigenvalues, because they are just the way structure default. Not anything to do with the absolute responses. This is a mistake that you every now and then you see that people are looking at the results of eigenvalues, and then they're measuring, okay, how much is the amplitude here? Don't do it, because it's not related to final responses. And why not? Well, it's not related to any of the responses because this vector can be multiplied by any number you want, and still it fulfills the original equation. I can multiply that by, say, 10. Big amplitudes, right? Nothing to do with the real responses. Or 0.001, very small. Makes no difference. It's just the way that matters. Weight is the only thing that matters for us. How is it work? Okay, let's take a look. So here is my original structure. You know, based on these results, I can tell that the first node, this one here, is moving relatively to minus direction, 2 units. So it's moving here, here. You got it? Then the second one is moving also the same direction, the negative direction, but not as much. So it's moving here. Third one here, this is the value. So it's moving a little bit of this direction, like this. And this one here is moving a lot of this direction. So this is the deformation mode. What is that? Yeah, I don't know what that is called, but it's this. You got it? Okay, what about the next one? How the next one look like? Okay, well, I'm not computing the next, but I'm computing the last one. Here, you know, maybe better to take this off. Let me see. Yeah, look at this. So, in this case, first one is moving a little bit of minus direction like here. Second one is moving the positive direction. This is moving the negative direction. This is moving the positive direction. So it's kind of like a wave traveling through the structure. This is a deformation wave, nothing else. Now, if I would ask you about what is the physical interpretation of eigenvector, this one here, do you know what's the answer?
How the system is deformed?
Yeah. Okay, so others, can I ask this? You sure? So if the next in-class quiz is saying, we're asking, what is an physical interpretation of eigenvector? Can I do it? You sure? Do you know what's the answer? Are you 100% sure? Okay, let's move on. Physical interpretation of an eigenvector. What a surprise. So here it is. So, absolute displacement associated to eigenvalue. So the way that a structure can deform defines damping of the structure. No clear physical interpretation. And sorry that my circuit is off, so I need to put it back on. Hold on. Okay, so it's back on. So these are the options. Okay.
Still, first question is up here.
Oh yeah, you're right about that. So let me move on. So the next one. Physical interpretation of an eigenvector. Eigenvector. Okay. So, of course, the candy pack goes around again if this is 100% success rate. Of course.
Why the answers?
Some answers are different.
Really? Let me see how they're different. Okay, strain distribution within a structure. Strain distribution. Here's useless. C is incorrect either way. It's left only three choices to select. So now the choices are absolute displacement associated to eigenvalue. Absolute. Okay? So is the way the structure can deform. No clear interpretation because the C is inconsistent here.
In Socrates, we don't have this item. If you check the Socrates.
Really? So what
We
it
don't
is?
have, we have there are these things.
Only two options.
Two options. What are these two options?
Ei osa VR Stefan and ei osa Max.
Oh yeah, I see that this is a big stop because they are mixed. Do nothing because this is inconsistent. I don't understand. I thought that I fixed them all, but obviously I did not. Okay, don't answer.
I answered according to the slide.
That's fine. So
It seems like
yeah, so
A option.
let's leave this and I will ask this next week. All right? What is the correct answer?
B.
B. In what
Here slides.
B. Yes, of course, B. I was my mistake. I was confused. B. So is the way the structure can deform. That's what we are after all the time. We don't care about the responses because what is needed in the response is the model coordinates. Is the very essential part. We only know the half of the story, less than half of the story. Okay. Now, just a few important information. These eigenvectors, as I said, that they can be multiplied by any number you want, and they still fulfill this original equation. And actually, they are multiplied by a number because you have to use a certain kind of scaling in order to make the mass to be identity matrix, and in order to have eigenvalue in a stiffness, in a diagonal of the stiffness matrix. And typically, this scaling is called normalization. And when you're normalizing this respect to mass, it's called, surprisingly enough, mass normalization. So you're normalizing your values, your eigenvectors, such the way that your mass matrix associated to modal coordinates will be identity matrix. And that requires that the solution results that are coming out from the eigenvalue analysis may be or may need a number that they are multiplied with. Now, how it goes then? It goes such the way that you use this equation, and in this equation you're solving the alpha. The alpha is just a scaling number, because the equation can be multiplied by any number you want. So let's multiply. By what number? Number that makes sense. Number that leads to the situation that the mass eventually will consist of identity matrix. Okay, so let's use a eigenvector and corresponding eigenmode that is associated with the second ID number. So let's take this one here, multiply that with my original mass matrix, and here is again the deformation mode, and then I have here these unknown scaling factors. One equation, one up. So I can solve my scaling number, and the scaling number is square root 1 divided by 5. Fine. So that gives me a new kind of, the same way that the structure deformed, but now scaled with the mass. Alright? Then I can do that for the second mode, which is a mode ID number 4. Again, I have this equation here in the modes, unknown, my original mass, my deformation mode, my unknown. I can solve it, and this time it's turned out to be 1. Alright, so these are my scaled deformation modes. Now look at this. This is my matrix representation of deformation. So what is telling me? Each one of the columns here are associated to ways that the structure can deform. How many ways I have in this matrix? So what's going on? So is the mic broken? I'm not using mic. Oh, so what's going on? So why is that we don't communicate? How many different ways is inside of this matrix? 2, correct. 2 ways. 2 ways because of the 2 columns. And then how many nodal degrees of freedom? 4. Correct. So that's what it is. So each one of the nodal degrees of freedom, how they are moving with respect to each other, is telling by these numbers. When you add them together, hold on. What is this?
Control Z.
No.
Just drag it.
Oh my God, I've never seen. Okay, now it's disappeared. But what was the thing that I was about to explain?
Nodal degree 4.
4 nodal degrees of freedom.
Okay, 4 nodal degrees of freedom.
4 rows.
Okay, don't remember that so clearly, but what we have here is that, I remember. This is the way that the structure moves. What is a way? This is a relative displacement, nothing else.
Relative displacement.
Relative displacement, yes. Okay, now once I do this, once I take these 2, let me see if it's able to make me any drawings here. These 2 ways that the structure deform and multiply, using them to multiply them with the mass matrix. Look, I have here 2 by 2 identity matrix. I'm only using 2 nodal coordinates. Originally I have 4 nodal degrees of freedom. Now I'm just using 2. I'm not going to get exactly the same solution, but I'm estimating that my solution is good enough. How the stiffness look? These eigenvalues are now in the diagonal components. Okay, that's how it looks. Now my final, when I'm expressing my equation of motion using this technique, this is how it finally reads. This is my modal inertia. This is my modal stiffness. These are the external applied forces that I have converted to be expressed in modal coordinates. Now I can take, this is how it finally reads. So I can take any, well, this time, one out of the two modal coordinates and solve it without knowing anything about others. So that's beautiful too. That's quite beautiful. Isn't it? It is beautiful. It is beautiful. So that's how it goes. Now, this is the equation that I can use in order to solve P. Alright? From P dot dot, I'm going to integrate P. What? How that is related to my original problem, because that was after this U bar F. Remember that? In multi-body system dynamics. Is this a dead end? Can I go back here to there? Yes, of course. Because remember, this relation, P goes here. It's telling me U bar, and that's how the whole story goes. That's how it goes. What do you say? Makes sense. Really? Sure about that? Because I'm not sure by myself. So let's take a look again. So we got force first, modal coordinates, and then from modal coordinates we get this one, and then here, and then, yeah, that makes sense. That makes sense. That makes sense. I think this is correct. Very nice. Very nice. And this tells you how you can go back to physical nodal degrees of freedom. And not just the nodal degrees of freedom, because once you have a nodal degrees of freedom, you can also tell how is each one of the particles within the elements, how they perform. How those goes? Well, shape functions. All right. Now comes something extremely important. Let me see. Yeah, we have a time to discuss about this. Now I have here an example. In this example, I need to make this a bit bigger. So I have a structure. This is something that you're very much familiar with. So this is a crankshaft mechanism. Now I would like to model one body as a flexible body. And the one body that I would like to model as a flexible body is this connection rod. Connection rod is connected to neighboring bodies with help of revolute joints. Two revolute joints. Okay? Now, if that's the situation, how is that I should select my boundary condition? In a finite element method, if you want to get rid of your rigid body models, you have to set the boundary condition. But how can I do it? The choices are that I don't do it. I don't compute, I don't set any boundary conditions, but instead I will take this connection rod, put it in a space, and compute the equivalence. That's exactly what I did in the previous case. Then the deformation mode looked like, well, they look like this. Second option, I will take a simply supported beam condition. And then I will compute the deformation modes. That's it. Now look what I'm after here. I'm looking after the way structure deformed. Right? That's my option number B. The final option is that I will set this connection rod, I will attach that to ground using one end, making as a cantilever beam. My question is, three choices, but what is correct? This is really, really difficult. Maybe the all-time most difficult question. Okay, in class quiz. How to set the boundary condition? What's going on? This is different again. Now, let me see. So method, okay, so it's all right. Okay, how to set the boundary condition. Now this is not inconsistent. This is consistent with the text in my slide. So, A, B, C, something else. A, B, C, something else. So what do you think? Is it gonna be candy time?
Yes.
I don't think so. So yeah, if it is candy time, what is it you say? What is correct?
B.
B. You say B. I say no comments. Okay, what are the others? What else that you say?
Respect.
Respect. Okay, so let me take a look. Let me check my Socrates 20. Okay, enter your answer and then we will take a look. You all done? You're done. Okay, in 5. Okay, more is coming. No, 3 only is missing. In 3, 2. Okay, can I just close this? 1. Okay, that's it. Everything is correct. You know, it doesn't matter what you select, it's correct. Now, wait a minute. Doesn't matter what you select is correct. This is against the common sense, big time, big time. How come? Because think about that. Remember what they teach you in a USIS course. You've been in a USIS course already. He will explain this to you later, but you know, these boundary conditions are associated to frequencies. How come it's possible that you can select it in 3 different ways and still get the same responses? Is this incorrect? What makes this possible? Because this is so much against the common sense. Well, this is something that we need to stop and look at this together, because you know what matters here is final destination. Not the way to final destination, but the final destination. Okay, let's look at this then. So if the final destination is what matters, let's make this in a way that we are looking at a cantilever beam like this. A cantilever beam that is pushed upwards. Okay? Now if I'm going to use this reference condition, if I'm going to use this boundary condition, it's clear how is my body reference coordinate system. It's going to be, let's change the color here. It's going to be, it's going to be here, right? And let's say that my global coordinate system is here. And now if the deformed configuration is like this, you know, this point here, I can first get by traveling here and then here. All right, makes sense. What about the second set? Well, let's change the color then. In the second set, again I have the same, this is not a good color, this is a good color. In the second set I have the same deformation here, but because the way, you know, this is set, now my body reference coordinate system is actually no longer same orientation, but is rotating. All right? I'm traveling here to here, and I end up to be in the same location. The final configuration, let me change the color again, gray. Okay? Again, the deformation is like this, but this time the body reference coordinate system moves here. So I travel here and then here. What matters is this. It's all the time same. The road is different. Road is very different. But the final destination is same.
How it differs doesn't
What is that? So what was that?
matter. How it differs, the difference doesn't matter.
How is the first?
It differs in the same way, but I mean.
Because if you look at, you know, this is a bit confusing. If you look at the deformation way, deformation mode is practically same. It's not that much different here. If you look at this mode and this mode, they look more or less same. The only difference comes how is a reference condition. And this reference condition, this coordinate system, how that is associated to deformation, that is called reference condition. And that is defined by your boundary condition in your finite element model. Now you can look something, you can, I've been mentioned that you need to know where the name floating frame of reference formulation is coming from. But what the heck is this floating? Where this floating is coming from? Is it or is it not? Tell me. I can tell you that yes and no. So, and this floating is associated to this boundary condition that is shown here. In this boundary condition, I have no boundary condition. All right? So what if I have this kind of boundary condition, and if the body deforms, what happens to my body reference coordinate system? The body reference coordinate system is detached to material point because it's not following the translation, it's not following the rotation, but it's detached. And this is where the name floating is coming from. Because this is the one possibility you can set your boundary condition as no boundary condition. And then your body reference coordinate system is floating with your body. It remains in a one material point, but as soon as there is a deformation, it is detached to form its original material point. How much it is detached? Depending on how much this particular deformation mode is contributing and how much others are contributing. But that's where the name floating is coming from. Remember, the name of the method is floating frame of reference formulation. Floating. You got it? Can I ask where the name floating is coming? Can I? Seriously? So if there's a class quiz asking where the name floating is coming, can you answer that correctly? This is, I cannot read you, so this is like saying that, okay, so what it is, can you or can you not? You can, because of can do attitude. Correct. All right, so let's take a look. Now, here, all the methods leads to roughly same responses because we are looking at the deformation mode. They are associated to different frequencies. But, when you look at these linear deformation associated with this reference condition, frequency is always associated to this reference condition, and reference condition is the one that is changing from one to another. That's why natural frequency is changing as well. But what we are essentially interested in is the deformation mode. Okay, my question is this. What the floating means in a floating frame of reference formulation? It means that the formulation is still under development, so it's floating, it's not yet reached the convergence. It means that the body inertia can change, that the body mass can fluctuate. B option. It means that the strain within the flexible body can be defined easily. It means that the body reference coordinate system can move from a material point of a body. Would you like me to repeat the previous story, or are you just good to go? You're good to go. Others, what are you saying? Yes. It's okay. So, okay. Now, unfortunately, this is our last opportunity to gain 100% success rate. And isn't it a good tweeter if I say that, look at my outstanding student, they were able to complete it 70% success rate? Not a good tweet. I'm really sucks with these tweets. It's really is difficult to use that. Do you use Twitter? What is that you use that? Instagram? No? YouTube? No? You have your own YouTube channel. Okay, because I was about to subscribe to your channel. Okay. Okay, so what do you say? Now, options are, what the floating means in a floating frame reference formulation. It means that the formulation is still underdeveloped. So it's floating towards the final configuration, or final form. It means that the body inertia can fluctuate. It means that the body mass can change. Mass can change. It means that the strain within the flexible body can be defined easily. And the final one, it means that the body reference coordinate system can move from a material point of the body. One is correct. What is the correct one? Okay, so we have now 8 students that are still thinking. Okay, what is the success rate? 70. 90, but it needs to be 100 because otherwise the tweet is not good. So I don't know how to put it in 100. Can I cheat here? Is there a way to cheat here?
Yes.
How can I cheat it?
Redoing the quiz.
Redo it.
Yeah.
Oh, yeah. That's the way we can do it. And so we go back and then do it again.
We say answer first, we go back, and then we do again.
Ah, okay. Okay, that's nice. That's handy. Okay. You done?
And then you can write in Twitter that we have such a stupid student that.
Yeah, of course, that's not even true. Think about this. I know we're going to discuss about this when I'm speaking about the career counseling. NUT is one of the high-ranked universities, and finding a way to high-ranked universities is difficult. So it's not just possible that you guys, there's no other way that you're just all outstanding students. Anything else cannot be true. Cannot be true. Okay, now we're done. Okay, so is it going to be yes? Okay, so how do I go back?
Previous.
Okay, so nothing to do with the strings yet. So we haven't discussed about the strings. And by the way, they're not easy to define. They are not easy to define. It's not going to help you at all. But what it means is this, that if you have this body like this, and you're introducing deformation because of these forces or these forces, then this deformation look like this, and the body reference coordinate system is detached from a material point. That's where the name floating is coming from. So it's kind of weird concept. So it is traveling, it is translating, and it is rotating within the body, but it can also detach from the material point if the deformation takes place. With that, let's close for today. Next week, I'm going to discuss a little bit about another way to describe this deformation, which is very often used method, which is called Craig-Compton method. And then we're going to start preparing us to midterm exam. And on Thursday at 1:15, audience swap, Art of Bicycle Dynamics. What was that room again? 1-3 something. Be there. I will take you candy. I will take some candies to that place. So be there. All right. So let's close for the day, and see you on Thursday.